So welcome everybody. Today it's the first lecture of the course of Raffaele about naturalness in quantum field theory after LHC. Raffaele has a long CV, has been hired here at IPhT in 2019. He had the PhD in Scuola Normale di Pisa in 2013. Then he went for a postdoc in Princeton, then in Stanford, then at SLAC. And he's an expert, a lot of things, including dark matter, Higgs boson, flavor physics, action, and last but not least, machine learning. So, Raffaele, it's
Well, so thank you very much for the invitation. Well, thank you all for coming. I wasn't expecting so many people, and also I wasn't expecting such a high level, so I'm afraid that some of you will be bored at the beginning, but well, I'll try to jump between more basic statements that everyone can understand, advanced statements that will try to ensure that that all the senior people I see in the audience will not be too bored. Well, we're going to talk about two problems that have existed in particle physics for decades, and for the longest time we thought we knew the solution to at least one of them, but now we're not so sure anymore. And the first lecture, or maybe 1.5, will mostly be devoted to stating the problems precisely. This is something that maybe 10 years ago I would have needed to do, but after the most appealing solutions have started to look less and less appealing because of experiments, some people have started to question the problem. And many of these, let's say, doubts that have been raised on the nature of the problem are just due to the fact that usually it's not formulated properly. So some people attack what are essentially wrong statements about the problem, but there is a few clean and pristine ways of presenting them that make very clear that these are questions that are concrete and rooted in experiment and we should think about. And so the first lecture I think might be boring to some of you because it's just the precise restatement of known facts. But then after that, this last part of the title of the course, so after the LHC, is essentially the part that gives me license to go as crazy as I want. So I'm not going to tell you only about explanations that have been developed for decades and that the community agrees are interesting and worth studying, but I'm also going to tell you about more speculative ideas that have been developed more recently, going even all the way to ideas that for the moment exist maybe only in 2 dimensions or only at the conceptual level and are not as developed as those that can go all the way from to make a prediction for experiment. So, okay, after this long introduction slash disclaimer, let me get a bit more into something concrete. So, as you know, we have these 2 parameters in the standard model Lagrangian. One is the cosmological constant, and one is the Higgs boson mass squared. So, for the experts, there is a precise sense in which these 2 parameters are the most important in describing nature at low energies, because they're associated to the 2 most relevant operators in the Lagrangian. So by just RG flow, these become the 2 most important quantities at low energy. And in fact, I mean, it's not an accident that they determine essentially how the universe looks like macroscopically. So the cosmological constant determines what's the largest size that the observable universe can have. And the Higgs boson mass squared determines a bunch of things: the range of weak interactions, the mass of all elementary particles that have a mass, and through these also the existence of complex chemistry, nuclei, and ultimately life as we know it. So the value of these 2 parameters is really critical on for how the universe looks like at low energy, and in particular for our existence. And we measured both of them. And the cosmological constant turns out to be close to 10 to the minus 4 electron volt to the 4. And the Higgs boson mass 100 G squared, so the mass squared. For the cosmology, so I'm going to use all the time the particle physics definition of the cosmological constant, and when I do otherwise, I'll let you know. So for me, the cosmological constant is a quantity that has dimension of an energy density or a potential. So as I said, essentially all of today will be devoted to stating the problem precisely, but let me start by stating it not precisely. And the issue here is that this is what we get from experiment. But if we do an estimate, and let me stress the word estimate, using what we know of the theory of the fundamental interactions, essentially, when I do this estimate, I'm using only the most basic thing I know. So I'm only using the selection rules of broken symmetry. So I'm using a principle that in principle works in physics. Every time you use it, it works so well that, I mean, it's what we use also to build buildings and planes, and I mean, we use it in every science all the time. But if you apply to these two parameters, you get something completely off. So the experimental value of the cosmological constant over this theory estimate that I'm going to make precise in the rest of the lecture is about 120 orders of magnitude too small. And similarly for the Higgs boson mass. Not so dramatic, but almost. And so naturally, well, we want to understand why. On the one hand, because these parameters are so central to our description of the universe, but also because we've encountered similar tensions in the past, and they were always signaling something interesting. So something similar was happening if you try to compute, for example, the self-energy of the electron in classical electrodynamics. There is a contribution coming from the electric field in a sphere around the electron. And this contribution, as you make the radius of the sphere smaller, grows. And so at some point, you are finding a contradiction. So you're finding that your theory estimate for what the mass of the electron should be becomes bigger than the electron mass that you measure. And the resolution of this tension was just that when you hit precisely this size in natural units, well, you essentially discover quantum field theory. So you start making electron-positron pairs, and you find that there is a new symmetry that emerges in this more complete description of electrodynamics that turns this apparent divergence into a logarithmic contribution. So studying such a problem in the past didn't directly lead to the development of quantum field theory, but was one of the first hints that something interesting was happening. And I could give you many more examples. I could also be more precise about this electron example, but I mean, I'm not really here to teach you the history of physics. So if you're interested, there's plenty of it in the notes that I will put online. Rather, I mean, what I would like to do today is, on the one hand, make this estimate more precise. So I stress that it's an estimate, because in the standard model, you cannot calculate either one of these parameters. So in the standard model, there is no problem at all. These parameters are just measured. There is no way that you can actually calculate their value. And these huge discrepancies that you find, in some sense, are moot. And so what I want to do today is, on the one hand, show you that this is the case in the standard model, and on the other, tell you why it's still a problem, even if in the standard model there is no way you can actually do this calculation. Before doing that, well, let me give you a preview of what the rest of the course is going to be. Again, in the interest of not boring all the more advanced people in the audience. Because the reason that we like to think about these problems is really that no matter what's the explanation for this tension, it's going to teach us something interesting about nature and kind of dramatic about nature. So it's not going to be a small incremental addition to our knowledge, but whatever explains this tension is going to really change the way we think about fundamental interactions. And so I'll make you a list of possible explanations for this tension for the Higgs mass. And then, well, I'll tell you also which ones of them apply to the cosmological constant. And so the first option, which is also the preferred one of many of us, so this is for the Higgs mass, okay? And then we will have some parallel column for the cosmological constant. So the first option is that there is a symmetry at some scale close to the mass itself. And this symmetry essentially changes this estimate by orders of magnitude, because essentially screens the Higgs mass from high energy contributions that are responsible for this large discrepancy. So at the moment, I'm going to be sloppy in this list. As I said, it's a preview for the people that already know all about this. But then essentially the rest of the course will be going into each item of this list and making it precise. So this is option number one. Of course, if there is a symmetry close to the Higgs mass, there should also be dynamics or a lot of new particles realizing it. And for now, we have not seen it, but it's a possibility. For the cosmological constant, on paper, it's also a possibility, but in practice, we have no idea how to do it, because already, if this symmetry, say, appeared at the electron mass, then the natural value for the cosmological constant would be something like the electron mass to the fourth, or maybe a loop factor. Let me just forget the loop factor, which is already order tens of orders of magnitude in tension with experiment. So this first option, it is maybe conceptually a possibility for the cosmological constant, but not quite. Then, well, another option is that the scale of quantum gravity is much lower than we think. Because secretly, when I do these theory estimates, what I'm doing is that I'm saying that since these two quantities are not protected by any symmetry in the standard model, they're just proportional to the largest dimensional full scale that we know about, which is the Planck scale. So when I claim that there is this tension, all I'm doing is that I'm using dimensional analysis and sticking on the right-hand side the biggest dimensional full scale that we have. And so one possibility, again, viable for the Higgs mass, but not so much for the cosmological constant, is that secretly Planck, if you define it starting from the Einstein-Hilbert action as the dimensions of a web, meaning that it has the dimensions of a mass divided by a coupling. So here I'm restoring units to H slash. And so it's possible that this web corresponds actually to a mass scale which is much smaller and maybe close to the Higgs mass. So that now this estimate becomes what you expect for the 100 GeV. And again, for the same reason that we said for the symmetry, this doesn't quite do anything for the cosmological constant. And well, as you can see, these were my two, let's say, most conservative options, and they're already pretty dramatic. So I'm telling you that maybe there is a new symmetry of the fundamental interactions, or maybe the scale of quantum gravity is 17 orders of magnitude smaller than what we think. Another option, which is roughly the only one that works for the cosmological constant, is that there is a landscape of values for these two parameters. And what a landscape is what we will talk about in great detail towards the middle of the course. It could be a multiverse, where the fundamental parameters of your theory vary from universe to universe, but it could also be entirely contained in our universe. We'll see that later. And well, if you imagine that there is a landscape of values for these parameters, some of these values realized in the landscape might be accidentally small. So here we are effectively, we're assuming implicitly that we're in a theory where these parameters can be calculated. And so you're going to make your calculation and you're going to get that these two parameters, you get contributions of the order that you expect. So with the largest mass scales in your theory appearing on the right-hand side. But you're also imagining that these order 1 numbers change from one universe to another universe, or from one realization in the landscape to another realization. And so there are some where these numbers, even if individually are order 1, have a sum that is much, much smaller than 1. So in some instances, rare instances, these parameters are accidentally small. But of course, we still need to explain why we see precisely a realization that is so accidentally tuned. Because in most realizations, they're going to be their natural value. So order the biggest mass scale in your theory to the appropriate power. And there are many ways to explain why we see such an unlikely value for these parameters in a landscape, ranging from an act of God, which is my way of calling anthropic arguments, all the way to some dynamical mechanism that explains why the universe evolved in such a way that today we see small values for these parameters. And this would be, in some sense, the center of the course. So seeing what you can do for these parameters in the landscape. And it's also roughly the only possibility that extends also to the cosmological constant. And now, well, let me come to the more speculative options. Well, more speculative option number 1 is that these parameters are never calculable. And what I mean will be easy to understand by the end of today. So you can make these estimates based on dimensional analysis, but you can never compute any of these order 1 quantities in your theory. You can only measure the number that's given by the sum, and that's it. So there is no real physics problem. This seems kind of harmless because it's what we see in the standard model. But in practice, as far as I know, we don't know a theory of quantum gravity where these parameters are not calculable, because more or less to make sense of it, we need supersymmetry at some scale, which makes them calculable, but the experts can correct me if I'm wrong. In any case, well, I just want to point out that saying this is much less harmless than it sounds. So it's not easy to write a theory that incorporates everything we know about nature where these parameters are not calculable. Finally, well, there are 2 more options that are also a bit out there. The first one is that there are no new mass scales that are coupled to the Higgs mass strongly enough to enter in these estimates. So essentially, all the couplings of these Higgs mass to these mass scales are tiny. And you can always engineer such a theory, except for gravity, because the coupling of gravity to the Higgs is fixed. So you would still expect all these m Planck squared type of contributions, unless you're able to write a theory of gravity with no scale, which is much, much harder than saying the words. The only, let's say, sensible example I know of is in two dimensions, and it's not even an example where gravity has no scale, but it's just that M Planck enters your calculation not as a massive threshold, but just as a parameter in the phase of the S matrix. Maybe we're talking about this, maybe not, because there's some obvious reasons why this 2D idea cannot be extended to 4 dimensions. But it's still interesting to contemplate these options, because another attempt along these lines in 4D this time is really to make gravity scaleless. The problem there is that you end up with a ghost. So again, we might or might not talk about it, because as far as I know, at the moment, no one has been able to make to make sense of theory of gravity without a scale like M Planck. And finally, maybe the most interesting one from the point of view of our intuition about quantum field theory is a possible UV-IR mixing, which I mean in a very broad sense. So under this umbrella, I essentially mean 2 broad possibilities. One is that truly the fundamental theory at higher energies doesn't like the way we use effective field theories. So you cannot integrate out degrees of freedom in the usual way, but there is always a fundamental way in which high energy quantities fit into low energy observables. And I mean, you might think that this is philosophy, but actually interestingly, there is one concrete example of this precisely for the mass of a scalar in non-commutative space-time. And this is, I'd say, a very fascinating idea that twists completely the way I think about quantum field theory. You will see if we have time to talk about this that it's completely crazy. I mean, you can integrate out stuff, but at the same time, you cannot write an effective theory of what you integrated out. The problem is that it breaks Lorentz symmetry at order 1. So it's a cute idea to contemplate, but at the moment, it doesn't work at all in nature. The second option is that maybe the consistency of quantum gravity forces these 2 parameters to be small in the infrared. And for the case of the cosmological constants, there are already conjectures that show how the Sitter space, so the case where the cosmological constant is positive, might be in tension with string theory. There are even conjectures that go farther away and try to squeeze you also from the opposite side, so where the cosmological constant is negative. For the X mass, I'm not aware of anything like it, and at the current level of my knowledge, I would be surprised if something like that existed, simply because I would be surprised that the theory of quantum gravity cared about the mass of a random scalar in a random sector, but I don't know. So summarizing this very long introduction, so we have this long list of options for the X mass. Roughly, a couple of them carry over also to the cosmological constant. And the bottom line of this first, I don't know, half an hour, I'm going way too slowly. This first half an hour of the course is that, as you can see, I mean, no matter what's the answer, you're going to learn something pretty dramatic about nature. A new symmetry, the scale of quantum gravity is much lower than you're expecting. Maybe you don't live in a single universe, but in a vast multiverse where the fundamental parameters change from universe to universe. Maybe there are some parameters in nature that you can never calculate, and the 2 most important ones are 2 of them. Maybe gravity doesn't look at all like you expect it to be, or maybe quantum field theory doesn't look at all like you expect it to be. Yeah, so this, I would say, concludes my long introduction. Maybe what I want to add, again, as a teaser for what's coming next, is that when it comes to the symmetries idea, I'm going to talk about the traditional stuff, so the symmetries that you all know can protect, can stabilize a mass hierarchy, so scale invariance and supersymmetry. But I think towards the end, I'm also going to talk about something newer. Because again, there is a very fascinating solution in 2 dimensions for the Higgs mass. So I'm sorry I kind of moved into the CC column, but this one refers to the Higgs mass. There is a duality between the Ising model and itself, which leaves the point where the mass of the boson describing the low energy excitations of the system is 0 stable. So essentially there is this transformation that moves the Ising model to itself, but in a very non-trivial way, that leaves stable only Mx equals 0. And this can be translated into modern language in terms of higher form symmetry in 2 dimensions. And again, there is no, I mean, there are some obvious obstructions in generalizing these to 4 dimensions that I will mention, but I think it's an interesting enough idea that opens up a whole box of novelties to be mentioned, because maybe these symmetries that us as BSM people are not so used to think about might eventually end up playing a role. All right, so this is roughly an overview of what's waiting for you in the next, I don't know, however many hours, but not today. So today, I'm sorry for the more advanced people in the audience, but today it's entirely about stating the problem. And again, I mean, as I said, 10 years ago, I wouldn't have had to state the problem for 1 hour, but not all human history is continuous progress. So, let's see. So as I was saying, in the standard model, you cannot calculate these 2 parameters, but you can make the estimate I alluded to purely from dimensional analysis. And well, as I said, dimensional analysis are really just the selection rules of relations. And what comes next is some pretty basic introduction to effective field theory, because, well, that's useful to get an idea of how powerful a broken symmetry can be and how its selection rules are useful to understand the value of observables. It's super well-known stuff for at least half of the audience, but since there is another half that I'm not so sure about, I'm gonna tell you this, but I'll be quick, okay? So start from any quantum field theory of your choice that since time lazy, I'm gonna write just in terms of scalar fields, but these phi's can represent any field. And imagine that you want to make a measurement at some energy much smaller than the largest scale at which you know the theory. Okay, M is the largest scale where you know that the theory is valid. Then you can always break the modes of the fields into two. So the light fields are those that have energies that are much smaller than M, and the heavy fields. Well, let me say that M is not exactly the largest scale when you know the theory, okay? It's some intermediate scale. Let's say you know the theory up to M star, and then you have some intermediate scale M, and you want to do your measurement at E, okay? And then I'm going to break down the theory into heavy and light modes. And then, well, I can always rewrite my path integral by breaking into 2 the integration measure. So far, I've done nothing. And I can also always do the integral over the heavy degrees of freedom and end up with some action that contains only the light degrees of freedom. And so far, this is just a definition. So And you might say, and rightly so, that I've done nothing, because 99% of the time this integral is impossible to do. But the nice thing is that the selection rules of dilations are so powerful that even if I don't know how to do the integral, this procedure is very useful, because I can always say, okay, so I know that this action can be written as some infinite sum over a set of operators. And, well, these operators are built out of the light fields. And I can build them in two ways. So if I actually know the high energy theory, as I'm assuming here, I can build just all the operators that are consistent with the symmetries of the high energy theory, meaning that some of these coefficients C here are going to be 0 just because of the symmetry of the high energy theory. If I don't know the symmetry of the high energy theory, and I'm a experimentalist that is stuck somewhere here, well, I'm just going to build them consistent with the symmetries of the low energy theory. Again, you might say, okay, you've done nothing because here you have an infinite sum, but here is where dimensional analysis or the selection rules of dilation come in handy, because let me, for now, I will not always do it, but most of the times I will, so let me stick to natural units. So in this case, all quantities have dimensions of energy or of length, and my operators in particular will have some dimension. For short, I'm just going to write the dimension of the number, not the energy to the number. Then the action, well, the action, we know that is dimensionless. We set h' to 1. And so, okay, we know also the dimensions of these coefficients, which is just b minus the dimension of the operator. And so now I can ask, what's the contribution of each term of this sum to my low energy observables? So this part here, I can estimate using dimensional analysis and doing a measurement of this energy E. So this is going to be E to the delta minus T. And well, well, not yet, but I will in a second show you that these are the selection rules of dilations. Okay, to some of you it's obvious, but I will show it to you explicitly when it comes to the X bus. For the CE, we can again do an estimate based on dimensional analysis. So we know there's going to be some dimensionless number times m to the e minus delta, plus some other dimensionless number times some other mass scale that you can have in the theory, the same power, and so on. So essentially here I'm just putting all the scales in the theory with dimensions times dimensionless numbers. And by choice, I mean by my initial assumptions, m is the largest scale that I have to consider in this low energy theory. So it's convenient to introduce a dimensionless version of these operator coefficients, which are just what you get by factoring out the larger scale. So in the end, if you put together these two-dimensional analysis estimates, you're going to have that a typical term in this sum contributes at low energy as E over m to the delta minus d times some dimensionless number. And well, if you have a symmetry that's telling you that some operator O sub I is not in your low energy theory, this G will be 0. If you don't have any symmetry, a priori you expect it to be order 1 because you just wrote down the most general possible expression for these coefficients as a sum of the quantities with the right dimensions. And so for the operators that are in the spectrum, so with these G's being order 1, you see immediately that you don't need to consider all of them when you're doing a low energy measurement. It will depend on their dimension. So if the operator dimension is bigger than the spacetime dimension, the operator is called irrelevant, because its importance at low energy becomes smaller and smaller as you go to lower and lower energies. So you're going to have objects that contribute in this way to your observables. Then you have the marginal ones that are constant. And you have the relevant ones. Okay? Because of unitarity, the deltas cannot be negative. So the most relevant thing that you can have in your theory scales like this. And in the standard model, it's precisely the cosmological constant. And the second more relevant object that we have in the standard model is the operator related to the X mass. So this is what, I mean, as many of you knew, this is what I meant before when I said that these two parameters are the most relevant in the Lagrangian. Now, yes.
So then you assume that the X scales like the energy minus 1.
Yeah.
As a property.
Yeah. I mean, at this level, it's, yeah, I mean, I'm secretly in Euclidean space. I should have said it at the beginning. And yeah, I'm also assuming that everything is isotropic. Yeah, I mean, this is a measurement that you're doing in flat space in your lab at the LHC. Let's put it this way. Yeah, so well, this tool is interesting in itself, as you know, so it makes calculations much simpler, and I think this kind of tells you why. So you might not know anything about the energy description of the world. You can just have done a few measurements at low energy, but you can still reconstruct a Lagrangian that describes your theory. This is the reason why the Lagrangians that describe nature are simple, because if you have a finite experimental precision, you're going to have access only to a finite number of these operators, and at some point, you're not going to be sensitive to these suppressed contributions anymore. So this is interesting in itself. The reason why it's relevant also for what we want to talk about in this course is that it immediately gives you an intuition for what theories that you find at high energies are surprising or not. So for example, let's say that at this energy, at this low energy E, you were observing the theory of a single free scalar. So this theory is not surprising because you can always imagine that your high energy theory respects a shift symmetry, for example. And so all the other operators that you might have thought of writing down, like phi squared, phi to the fourth, etc., are not there, because when you do this integral over the energy degrees of freedom, are never generated because of the symmetry. There might be, of course, objects like this, but you might simply not have reached high enough experimental accuracy or an high enough energy to see them. So the fact that you see only this at low energy is not surprising. Another thing that is not surprising in a more non-trivial way is if you see just a free scalar. So there are a few ways to see that this is not surprising, but let me tell you the one that is least well known. So this theory, you might or might not know that it has an infinite number of symmetries. These symmetries are kind of trivial. They all commute with each other, but still there, and you can see it if you go to Fourier space. If you go to Fourier space, the Lagrangian is going to look like this. And now you can say, okay, this Lagrangian has the following symmetry. So if I rotate phi by any function of k that is odd, okay, then it stays invariant. And interestingly, any interaction that you add breaks this symmetry. You can see it again by going to Fourier space. So in Fourier space, you can write a generic interaction as some function of the n moment of the scalars in the interaction times the n scalars. And so times a delta function for momentum conservation. And so, well, from here you see immediately that the only Lagrangian that preserves this infinite set of symmetries is the free one, because if here you have only two scalars, then the delta function is such that the two momenta must be equal and opposite, and when you do the phase rotation, this sum of phases the sum of phases cancels. So you have so if you have two scalars, the sum of phases that you get in this term when you do the rotation just becomes e to the I alpha k plus e to the I alpha minus k. And so any terms with two scalars preserves this symmetry, any term with more than two scalars breaks it, because the delta function is not enough anymore to cancel all the phases. And so again, seeing this free Lagrangian with any mass parameter, also much smaller than the largest one in your theory, is completely unsurprising. And we're going to use this symmetry again soon. Finally, well, let me give you one surprising example, which is also close to what you have in the standard model for the X. Well, this one is surprising because lambda is breaking this symmetry, and you have this mass scale m in your theory, which I'm imagining it's also breaking scale invariance. Okay, so this theory on its own is classically scale invariant, but I'm imagining that at m there is something real that happens. So there are some masses, there is something propagating with mass m that exists. In this case, when you do the integral over the any degrees of freedom, you expect to generate also a mass term of the scalar at least at this order. And you know that this is the answer that you expect from dimensional analysis, so the selection rules of dilations, which I'm going to show you soon for the standard model. So big M and little m transform in the same way when you rescale all the spatial coordinates, because they have the same energy dimensions. And then you need something in front that breaks also this symmetry. And lambda is precisely the object that breaks this symmetry. And so observing all these Lagrangian at low energy is quite surprising for this reason. Just at low energy, you can do this dimensional analysis estimate and wonder why you don't see such a mass. If you started at high energies, then you would have to somehow engineer a theory that is breaking all the symmetries that protect the mass, but it's still not generating. In practice, mechanically, when you go do this integral, you're going to generate a mass term of this order. And this is the, let's say, proto statement of the hierarchy problem, which we're going to make more precise in a second. Before getting to the actual standard model and hierarchy problem and the more precise version of this, let me make a couple of comments that, again, are not really useful for the experts. The first one is that this construction is on solid ground, even if I went quickly. So essentially what we're saying is that we are imagining that we know the theory at some large scale, and then we slowly go down by integrating a momentum shell by momentum shell. So you start by integrating out something like this. And then you keep going. You integrate out then this other momentum shell. And so on. So it's a smooth procedure. There are no infinities anywhere. Everything is continuous in the coupling. And what you're doing by going continuously step by step is that you are essentially generating a flow. So as you keep integrating out momentum shells, the action is changing. You are first generating some S of M1, and then some S of M2, and so on. And it's changing in a smooth way. You can write differential equations for the parameters in the Lagrange. And this is, I mean, the way that Wilson thinks about effective field theories and the way we all think about quantum field theories these days. So computationally, it's more convenient to say I have my theory and then I compute loops up to infinite energy and I cancel the infinities. But this is very unphysical. I mean, what you really do is that we know the theory up to some scale because we measured up to that scale. And then we integrate out parts of this theory to get a simplified low energy description. So in reality, the physical, again, I'm sorry for the words here, people, but the physical way to think about renormalization is this. So it's starting from the UV, slowly integrating out, and you'll see that the couplings with the Lagrangian change. If you start from the IR and try to do loop integrals up to infinite energy, you're doing something that you're simply not allowed to do because you don't know the theory above M star. So you shouldn't be surprised that you have these infinities that then you kind of hide under the carpet. And I'm saying all this because since sadly most QFT books don't do Wilson, but do effective field theory bottom up, I'm going to show you the calculation for the X mass in this other less pleasant framework, which is much more convenient for doing the calculation, but much less transparent for physics. And I'm doing it precisely because I want to make sure that whenever you open a book and you see a wrong statement of the hierarchy problem, you can come back to here and rectify it. All right, so now, okay, we kind of have all the ingredients modulo the standard model Lagrangian, which again, to most of you is well known, but I will very quickly remind you of. And then once we write down the standard model Lagrangian, we can just use in a more precise way the symmetry considerations that went into this QFT picture to see what I meant by my initial estimate that the X mass should be M+2 squared or the cosmological constant should be M+2 4. So I don't know how you do for the break. I can.
It's whenever you want and you find that it is a good moment to stop.
Okay, yeah, I think this is a good moment because then, then what comes next is, yeah, it's better to break here. Okay, so since I got the question, let me mention that this symmetry I was talking about for the free scalar doesn't really have a name, so you can expand the odd function momentum to get the generators. The first one are the generators of translations, but the other ones are just derivative cube, derivative to the fifth, and so on. So you have this infinite tower of higher spin symmetries, but the algebra is trivial, so they all commute with each other. They're all derivatives. And I learned about this symmetry from Rattazzi's BSM lectures. They're very nice. I strongly recommend them. They're called BSM for millennials. And I don't think that, I mean, I'm not sure if it's something that he found out or he learned from somewhere else. And for the moment, it doesn't have a name. As we were saying during the break, we don't know, I mean, a theory of nature that realizes it because we haven't observed any free scalar, which would be quite difficult to observe since to see it, we need it to be interacting. But, I mean, the zeroth order point that you should get from this course is that broken symmetry are often more useful than realized symmetries. And that's what we're going to see now. So, first of all, a quick reminder of what's the standard model for those of you that don't think about it every day. And then we see what we can say about the X mass in the standard model, precisely. Okay? So I'll go quickly because I'm sure that sooner or later you've all seen the standard model. So the standard model has, right, this gauge group. These are strong interactions, weak interactions, or electroweak and hypercharge. And it contains a few fermions. I'm just going to write it in notation where all these things are while spinors, all left-handed spinors. And in parentheses, I'm writing the quantum numbers under the gauge groups. So Q is a doublet of electroweak interactions, is a fundamental of strong interactions, and it has hypercharge 1/6, for example. Then there is the electron doublet. More quarks, which interact with the strong group. And the electron. Well, it's traditional not to include in this list neutrinos. I think that they are part of the standard model, but since we're not going to talk about them too much in the following, you can think about this fermion content. So we have these three fields that are strongly interacting, are coupled to CD, SU3, and everyone is coupled to the electroweak group, but only these two fields are doublets of SU2. And then, well, the first part of the standard model Lagrangian is just describing the gauge sector. So you're going to have the kinetic terms for the gauge bosons of the four groups. So this is hypercharge, this is SU3, and this is SU2. And then the kinetic term for the fermions. With gauge interactions contained in the covariant derivative. Actually, since I'm going to use Wien spinors, let's do it this way. Well, I mean, if you want, I can write down explicitly the kinetic terms of the gauge bosons, but and the derivative of the fermion, but I don't think it's particularly useful. If you need it, you'll find it in the notes. What's more interesting for us is that, well, we know that these fermions are massive. We measure the mass of all of them now. But there is no way to write a mass with this particle content and this gauge symmetry. There is simply no way, because Lorentz contractions would want you to pair, for example, Q with QC, L with TC, but this break SU2. And so, well, what people have proposed a few decades ago is to add a new scalar doublet of SU2. So its quantum numbers are these. And this guy alone can give mass to the fermions through these Yukawa interactions. So first let me write is Lagrangian in isolation. And then, well, if we just write every dimension, every operator up to marginal consistent with the symmetries, you're going to have also things like this. And, well, Riccardo was kind enough to call me an expert of flavor physics, but you know immediately that I'm not, because I didn't tell you that these fermions come in 3 generations, and in reality, these Y here are 3x3 matrices. Okay, it's not going to be very crucial for what we're going to see next, but since we're doing this introduction to the standard model, why not? If we imagine that the mass in the Lagrangian is well, the mass of the Higgs boson here, this parameter here, is negative, then the potential for the radial component of this doublet looks like this. So its vacuum is not at 0, but it's somewhat displaced. To what we're going to call V. Okay, and this is how fermions get mass. So if you expand your theory around its true minimum, these interactions are going to contain also a part where this H doublet is constant, and you end up having a fermion bilinear that gives a mass to these fermions. A convenient way to see this is to use the gauge freedom in SU2 to write the Higgs doublet as this. Because in general, well, the Higgs doublet is going to have 4 degrees of freedom, so it's a complex scalar and it's a doublet. So something like this. However, well, you can always parameterize it non-linearly, so you can write this very same thing as in this way. So now the propagating degrees of freedom are these H and these pi's, and these are the Pauli matrices. And when you write it in this way, you see immediately that you can make an SU2 gauge transformation that gets rid of these propagating degrees of freedom and leaves you the doublet in this form. The difference between here and here is that here I'm already expanding it around its true minimum. So I'm going quickly because I'm assuming that you've all seen this multiple times. But if you've not stopped me, I mean, I can go more slowly and answer any questions. So now we have written in a slightly messy way on the blackboard the standard model Lagrangian. We have the gauge part, we have the Higgs, and we have the coupling of the Higgs to the fermions. We could, I guess, go in some detail in a few more aspects of the standard model, but I'd rather highlight one which is going to be important for our estimates of the Higgs mass, and then leave the other details for later if we're going to need them. So in this Lagrangian, the biggest coupling that the Higgs has is one of the Yukawa couplings down there, the one to the top quark. So as I told you, these Yukawa matrices are some 3x3 objects, but you can always, let's say, singular value decompose in this way. This is for y up, but it's valid for everyone else. And then you can always rotate these 3x3 matrices, these unitary matrices, you left and you right, by redefining the fermion fields. Clearly, well, this is going to do almost nothing to the Lagrangian. It's going to bring, so let me say that now you do some redefinition like this, for example. Okay. Well, obviously nothing happens to the kinetic terms of the gauge boson, nothing happens to the Higgs Lagrangian. The only interesting action of this rescaling is, other than the Yukawas, the kinetic terms of the fermions. So what happens to the Yukawas is that they become diagonal. So now you have something like, since I said we have 3 generations, you have something like this. The other thing that happens is that the interaction of one of the SU2 gauge bosons becomes off diagonal. So essentially, the mass eigenstates are not the same as the SU2 eigenstates. And so this gauge part of the Lagrangian, in one of its interactions, is going to get an off diagonal term, so something like this, where you have this is a dagger and this is a plus, and also this is a plus that I'll explain in a moment. And the plus is just as usual. And the V is what happens when you do this rotation. So V is U left for the up Yukawas, V left for the down Yukawas dagger. Because this rescaling here, I've done it schematically just for the up Yukawas, but you have to do it for all of them if you want all of them to be diagonal. So if you want to go to the mass basis. And same for the leptons. And so when you do this rotation for everyone, including the tau type quarks, you see immediately that this doublet is bothering you, because you would like to rotate away 2 left-handed unitary matrices, but SU2 forces you to treat the up and down left-handed quarks together. And so one of these, so these matrices must pop out somewhere else in the gauge interactions of SU2, and that's where they pop out. Okay. I'm sorry I've gone so quickly, but this is really very tangential to what we're going to say next. It's just to give to everyone that doesn't think about the standard model every day a more concrete picture of what we're talking about. The only important part of what I said very quickly and a bit confusingly up to now is this. So the biggest coupling of the Higgs in the standard model is this one. It's this Yukawa coupling to the top quark, which is roughly order 1. So now that we have the Lagrangian, we can ask what do we expect MH squared to be based on the symmetries at our disposal. And as I told you, the useful symmetries are the broken ones. The most useful symmetry, as we've seen, are dilations. So let me say that I rescale the spatial coordinate in my action in this way. Sorry. What happens is that, well, operators are going to scale with the inverse of the energy dimension. In particular, well, we can look at the two operators that we care the most about in this case. So the X mass and this coupling. Sorry. Yeah, let's. Here I should also add that there are some masses because I've expanded the X around its true minimum. So there is a part that couples the X to the fermions, but there is also a constant part. And since this is the biggest coupling of the X in the standard model, this is also the biggest mass in the standard model. And so naturally, we want to ask how these two objects transform. Well, to do that, we have to assign dimensions to the fields. Since the standard model is a perturbative theory, because a perturbative theory essentially means that interactions are subdominant to the kinetic terms. So if you want to know what dimension a field has in the standard model, you look at its kinetic term. So for the X, we're going to have something like this, and for the top, we have something like this. And we are in 4 dimensions. You want the action to be dimensionless. And so this immediately tells you that the X has dimension 1 and the top has dimension 3 alps. Okay, this is just the usual thing that you do for scalars and fermions in 4D. We do it so often that we think it's trivial. I mean, you should just keep in mind that this makes sense because the standard model is perturbative. If it was a strongly coupled theory, the actual dimensions of the fields compared to what you naively get from the kinetic terms could be order 1 different. There are even theories where fields have 2 kinetic terms, maybe one with 2 derivatives and a shared Simon's term, and depending on the energy you're at, one of the 2 dominates, and the dimension of the fields then smoothly interpolates between 2 limits. So, okay, I know this is a trivial, well-known thing to do, but one should always know what one is doing. But anyway, for the standard model, this is fine. And
sorry, but I mean, the standard model, of course, has sectors which are quite non-perturbative, like the color, and I mean and for that matter, as you said, the top Higgs coupling is order 1.
Indeed. Here we are secretly operating at energies, let's say, close to the Higgs mass. Okay, where QCD is perturbative. And for me, order 1 is perturbative enough, because I mean, this thing is gonna correct these dimensions at order y top squared over 16 pi squared. So within okay, so if you are at these energies, yeah, that's it's true. I should have said it. But indeed, I mean, when you go to lower energies, then this is not even the right Lagrangian to think about. And indeed, I mean, for example, this, I don't know, the kinetic term of the top can map to that of a scalar with completely different dimensions. I mean, well, the top you integrate it out, but other forks from which you would conclude naively that these are the dimensions that map to operators in the effective theory that describes the strongly coupled degrees of freedom that have completely different dimensions. So actually, good, the standard model is a good example of why you should be careful. But at the energies where we are operating, we are fine. Okay, so all this to say that these are, okay, this is the mass that we want to know want to make a prediction for, and this is the largest mass in the standard model. We now know the dimensions of the fields, so we know how, under a space-time dilation, this thing behaves. So you're gonna have so as you can see, the symmetry is broken, but I can promote the mass parameters to spurion fields. So essentially I'm giving them a fake transformation property that restores the symmetry. Sorry, to the -2. And the reason why this is useful is that now you know that if you transform also the mass parameters, the symmetry is restored. And so enforcing the selection rules of this broken symmetry is the same as asking that everything is invariant, so your observables are invariant if you transform also the parameters. For our estimate, we don't even need this level of sophistication. It's much simpler. So you want to estimate mx squared. And so on the right-hand side, obviously, you need something that transforms in the same way under the symmetry. So if you rescale MH and you get an S to the -2, on the other side, you need something that has the same properties. And so the selection rules of dilations in the standard model are telling you this, that mx squared should scale approximately like m top squared. This is not the whole story, though, precisely because of the higher spin symmetry that we said before, because if the x was a free scalar, really here there would be 0 in front of m top squared. So there would be no way to break the higher spin symmetry that we had before, and so no way to change the x 2-point function. And so for this estimate to make sense, we have to stick in front of m top squared something that breaks the higher spin symmetry that we had before. And what breaks it the most is the largest x coupling, so y top. This object under our higher spin symmetry that we had before transforms by getting a phase. Okay, let me Fourier transform just the x. And so the selection rules of and the mass, instead, the mass of the x goes to itself. So you want something that breaks this symmetry, but at the same time respects these transformation properties. So this is the higher spin symmetry that we call it. And so the only thing that you can do is this. Finally, if you restore dimensions to H slash, so here we are doing dimensional analysis in the simplest possible way, in natural units. But if you were to do dimensional analysis by restoring dimensions to H slash, then you would see that this is not quite right, okay? Because mx and m top are both a mass at the same dimensions. But y top has dimensions of H slash to the -1 alpha. So in reality, this can be true only at one loop. So that's why people sometimes say that phi has dimensions, because you can keep track of loop factors by restoring dimensions to H slash. So this is all you can say about mx in the standard model. So you cannot do better than this estimate. And I'll tell you why in the next half an hour. I think it's actually pretty good as time. So I think, well, from all this work that we did, that was probably, as I said, that 10 years ago would have been completely unnecessary, we learned two things, I would say. So the first one is that purely within the standard model, there is no problem at all, even at the imprecise level of just doing the dimensional analysis estimate. M top is 175 GeV, mx is 125. Everything looks fine. Okay. However, well, at this level, nothing stops you from doing the exact same thing that we did here, but including also Einstein-Hilbert. So we know that gravity is there. So why not adding also this term to the Lagrangian, sorry, to the action? If you do, then your estimate changes dramatically. If you do, your estimate becomes this. Again, the 16 pi square comes purely from restoring powers of H slash, because M Planck, as we were saying before, here it's a van, so it has the dimension of a mass over a coupling. Now, well, of course, your attitudes can vary regarding this estimate. You can say, well, you've been quite brave in extrapolating the standard model all the way to the Planck scale, imagining that there is nothing, and also assuming that this web also coincides with a mass. Maybe there is no mass here. Maybe there is something in between here and the Planck scale. But you see that this estimate essentially is telling you that the theory doesn't behave in the most naive way possible from the standard model, from the weak scale, all the way to the Planck scale. Because if it did, this would be the prediction for the Higgs mass. However, we're not quite there yet, because you can ask, okay, this is all very nice. You've used symmetries, dimensional analysis, you've been honest, you've done nothing wrong, but can you turn this squiggle into an equality? So is there any way to, at least for this contribution, to compute it, really put an equality here, an order one number, and maybe other contributions that I can measure independently of MX? And the answer is that purely within the standard model, it's impossible. Okay, so you can never compute the Higgs mass in terms of quantities that you measure independently of it. And now I'm going to show you in much more detail than you would like to why. Okay. So let's try. Okay. So now we've seen that dimensional analysis is maybe telling us that there is something weird going on with the Higgs mass, but we have done no calculation. So let's try to do a calculation and see what. So, since we don't want to spend the whole course on this, we're going to use a toy model, okay? Which is just the standard model in unitary gauge, where I've set to 0 all couplings except for the largest one. Okay, essentially, I spent the first hour telling you how interesting the hierarchy problem is, and the second hour telling you that there is no problem in the standard model. So you might wonder exactly what we're doing here. What we're doing here is that on the one hand, this dimensional analysis estimate still has a meaning. So if you extend the standard model, you might be able to compute the Higgs mass in a theory that is not the standard model and find an actual problem. So find that you can write the measured Higgs mass as quantity plus some other measured mass plus another measured mass and so on. And if these quantities are much bigger than what you see here, then now you do have an actual problem. So you have to explain why these coefficients here cancel exactly to give you something much smaller than the typical mass scales in your problem. And well, it turns out that we have strong reasons to believe that the theories that we complete the standard model look like this. And that's what we're going to see, I think, next time. So I'm not going to quite stop yet, but next time we're going to see that if you extend the standard model into a supersymmetric theory or an approximately scale invariant theory, this is exactly the case. So we're not in this situation anymore where we cannot compute the Higgs mass, but we're going to end up in a situation like this, where whatever you measure can be expressed in terms of other observables that can be measured independently and possibly be much bigger. Yes.
If you extend with gravity, this is what you get, or could you?
We don't know. So the whole point behind those crazy ideas in the first list is that we don't know. So if you do it in string theory, so you have supersymmetry at some scale, that's string theory, it looks exactly like this with M Planck here. With all objects of order M Planck. Okay? Not M Planck as M Planck, but these are masses like that can be at the string scale or whatever. So yeah, so this really becomes masses. Even if the theory in which you extend the standard model doesn't look nice and perturbative like SUSY with small couplings or string theory at small coupling, but it looks like that you go up and at some scale you turn into a conformal field theory where there are no particles, you cannot compute, I mean, it makes no sense talking about particles. One can show, I wasn't planning on showing it, but I can if you want next time, that you still get contributions to the X mass, to the observable one, that go like the scale at which scale invariance is broken. So you have to imagine that this is a scale where anomalous dimensions of field starting to change, okay? And then a bit above M, they reach some fixed point. So the whole theory goes to a fixed point. Even then, you get something like this for the X class. You get that it's calculable, and one of the contributions that you can calculate is proportional to this scale. Okay, since we are almost done with time, I think it makes more sense to start talking next time about these theories like supersymmetry or scale invariant theories where the X mass can be calculated. Now I just want to give you an example within the standard model of things that you can calculate, because naively you might say, well, doesn't this happen all the time? Every time that you want to measure a mass, you end up having to fix the Lagrangian parameter that you don't know by measuring the mass itself, and then you can never make any prediction. Well, the answer is no. And well, a famous example that I'm hoping that I'll be able to do in 10 minutes is the W mass in the standard model. Okay, so let's say I want to predict the observed value of the W mass in the standard model. So I would like something like this, where I can compute every single contribution to it in terms of things that I can measure independently. So what's the W mass? Again, we're going to do it at one loop. And again, as for the X, you're going to have diagrams that look like this. You can resum the bubbles, and in the end, you're going to get a propagator like this. I'm gonna drop the terms in the propagator that go like external momenta, because typically when you do these measurements, you're always attaching almost massless standard model terms on the left. So these terms are highly subdominant, and also at one loop they give you gauge dependent stuff. I mean, it's a huge pain that it's not worth to go into. Let's just focus on this term, which at the level of precision of our measurement is all we need. Okay, we will see it at the end of the calculation, but this is a disclaimer I want to give you at the beginning. So this bubble, of course, stands for any standard model fields that can be there, and I'm calling these pi's I pi p squared is just the invariant matrix element of a W of momentum P going to a W of momentum P. Okay, just this in case you want to redo the calculation. It's also in Schwartz and in a bunch of other places. So what's the W mass here? Well, the W mass is, as before, mW squared plus this pi WW evaluated at the pole. And as before, if you do the calculation, you'll find that this pi WW, indeed, you can write it as a bunch of quantities that you can measure independently, but you still have the problem of the Lagrangian parameter up here. Well, however, the Lagrangian parameter up here can be related to other parameters in the Lagrangian that you can measure independently. Actually, here I should have said the real part, IWW. Also for the X, I wasn't very precise. But what enters the pole is really the real part. The imaginary part is the decay width. So in the case of the W, there is some hope. So you can write the W Lagrangian parameter in terms of this cosine of the Weinberg angle and the Z mass. So if I can measure the cosine of the Weinberg angle and the Z mass independently of the W mass, I'm done. Okay, so it's not so hard to find a quantity that I can actually predict in the standard model. So how do we do it? It's relatively simple. For the Z mass, we do what we've done so far. So again, we write the propagator in this way. And then the measured mass is the Lagrangian parameter plus these one loop contributions that we can compute evaluated on the pole. So we can just invert, well, again, sorry, I should say the real part, okay? So we can easily invert the relation. So this first one was easy, okay? So we were able to, so now our goal is to write all the Lagrangian parameters. So is to write these two Lagrangian parameters in terms of observables. We've already done it. So for the Z mass, we've already succeeded. All this quantity with a hat are just quantity that you measure. So you can really attach a number. Actually, tell you the number to show you that we do not fool around in BSM. The number is 91.1867 times plus or minus a few MeV. Okay, so we're already doing pretty good, and I promise you I'm almost done. We're already doing pretty good. We're just missing CW squared. This actually is much more painful. It requires two measurements. Let me tell you which ones. So the first one is the muon lifetime. So the muon decays to a W, to an electron and an electron neutrino, and a muon neutrino. And again, well, in addition to this, you're going to have loop corrections of this type. Okay. There are loop corrections also to the fermionic legs, but they are subleading. And yeah, so from the muon lifetime, I'm not going to show you all the details, but you can measure a lifetime, and then allows you to measure what we call G-Fermi, which is an effective coupling. That's what you get when you integrate out the W. So it's essentially the coupling of this four fermion interaction. And if you write what's G Fermi, so what you get from these two diagrams, when you make the W infinitely massive, we get the following: P squared per 8 SW squared. I realize that I've not introduced many of these parameters. You can, well, for many of you, they are obvious. For the others, you can look at the notes. But these are just other parameters in the standard model Lagrangian. So you might feel that we went back to what we were doing before, but not quite. So now you want to take the zero momentum limit to get this G Fermi. So really, I should say, there's not an equality yet. Okay, only if t goes to 0. When t goes to 0, you get this. Again, the real part over mw squared. Okay, so on this side you have all Lagrangian parameters. On this side you have a measured quantity. Now you want to invert this to get SW and CW. You see on this side we have only MZ. This is MW, but it's a Lagrangian parameter, so we can rewrite it as CW squared times MZ squared. So on this side we have only a parameter that we already know how to express in terms of an observable, MZ. Then this cosine and sine of this W angle, which are the parameters that we care about. So all we're missing is E squared. And so to invert this relation, we have also to measure the gauge coupling, which we typically do from E plus E minus at the annihilations. Again, we want to consider also diagrams like this when you do it, which is going to tell you that the cross section for this process is equal to e to the fourth over 12 pi mz squared. So I'm going to measure it on the z pole. So here it's a photon, but also a z. Times. Well, sorry, no, I don't want to measure it at the z pole. I really want to measure it at low energy and then run it up to the z pole, so that only the photon matters at low energy, and then I run it up to the z pole, and so I can express my calculation more simply. Let me do it this way. Okay? I do it at some momentum. And this is observed. Okay, so I can, this is really e to the fourth observed over 12 pi, whatever momentum you're looking at. So now you want to invert this relation and this relation together in such a way that you can express E and SW squared or CW squared in terms of observed parameters. And if you do it, you're going to get the following. So you're going to get the E squared is the observed value, which is 1 minus this pi gamma gamma. And the angle is a bit more complicated. But I'm sorry, maybe I could have spared you much of these details, but just to give you an idea of why I'm not going to do the calculation for the X mass in the theories where it's calculable, because it has a much larger number of terms that you will see immediately from the Lagrangian. And already this simple calculation, as you can see, takes quite a while. I tried to do it quickly, not to bore you too much, but I hope that this did not make it incomprehensible. Okay, so at one loop, we have these two, plus we have the one for MZ that we wrote up there. So all we need to do is to plug these two back into MW here, and we are done.
Sorry, what is the SW hat?
Yeah, so SW hat is, let me tell you, yeah, so essentially, you can get it from here.
Yeah.
So it's secret, yeah, yes. Well, it's not the same, but it's what you get from this equation when you write SW in terms of G Fermi. Okay.
At tree level, I mean,
Yeah,
in
well,
terms
no,
of method,
yeah. So at tree level, you can use the tree level relation between the Lagrangian parameters to write SW in terms of GF, and then you use this one to write S hat in terms of, so essentially here, well, let's say here on this other side, you write GF in terms of SW at tree level, and then you equate this guy to this guy to get it on bottom. Yes, I should have, well, yeah, maybe I should have given you a few more details on the standard model Lagrange when I had the chance, instead of doing it now that we are at the very end. But there is a simple tree-level relation between G Fermi and this W hat, and that's how I can invert this equation. Okay, so essentially putting it all together, we have that we can make a prediction for MW. Which is the following. Here, I made a mistake on SW. Oh, okay, it's fine actually. Yeah, actually, let me tell you what's the tree-level relation that I'm using. The tree-level relation that I'm using is this one. Okay, so I'm using this relation on this side and then solving the equation. So finally, putting everything into MW, I'm gonna get, let me see where it is. I'm gonna get the following. I'll tell you in a second what this, well, yes, this pi r is a shorthand for, that I forgot to write now, I'll show you later. Okay, so this pi r is essentially this combination here that appears multiplying this factor in SW. Just not to write it in even more lines than I've done. Okay, so I apologize for the mess, but the bottom line is that within the standard model, in the case of the X mass, there is nothing you can do. So you can fix your unknown parameters only by measuring the X mass itself. But this is not a general statement. For example, already in the standard model, you can write MW purely in terms of measured quantities, also at loop level. And actually, it's important to include the loop level result. Otherwise, it would be off by many sigmas compared to the measurements that we have at left. The measurements that we have at left and that are now being improved by the LHC and the Tevatron are at the few MeV level. And these loop corrections are big enough that they are important. So if you do include the loop corrections, you're gonna get the standard model prediction of roughly, and I'm not listing the theory uncertainty. So all this painful calculation led to something well in accord with predictions. There is no tension whatsoever. And also, well, the difference that you see with respect to the Higgs boson is that when you write it in terms of measured quantities, they're all roughly of the same order. So the scale here is mz, which is comparable to mw. There are no masses that differ a lot by mw or mz. In the standard model, there aren't, period. But also, there is no way in this calculation to take mz to infinity without making also mw go to infinity. So there isn't a contribution at a different scale that would cancel it and create the similar tension that we've seen for the Higgs boson. Anyway, so I think
No,
yes.
sorry, where pi are? It's the first time that I see pi
Yeah,
r.
it's this one. Yeah, I only said it in words, but it's this object here
Okay.
that enters sine W.
Okay.
Yes, I will add it to the notes because I realized that I forgot to write it down in the notes. Anyway, so summarizing today's lecture, so the end was a lot of pain, probably unnecessary, but was aiming at showing you that in the standard model, there is no problem associated to the Higgs mass. It cannot be computed, end of the story. You do see some peculiarities in the effective theory, but they have nothing to do with observables. However, there is still this dimensional analysis estimate that is telling you that the theory that completes the standard model is not the most trivial possible. This estimate is telling you that if at some point your theory turns into something like the standard model is for MW, you will have a serious problem for the Higgs. So you're going to find that when you write it in terms of observables, the typical scaling frontier is much bigger than what you measure, and you'll have to explain why a bunch of potentially unrelated parameters cancel each other finally. Let me say that even if we spent almost 2 hours and a half together, if you feel that you don't yet know what the problem is, this is completely fine, because for now, we have not yet discussed a theory where there is a problem. That's what we're going to do next time. So next time, we're going to discuss secret symmetry and theories with scale invariance, where the dimensional analysis estimate that I showed you in the first half of the lecture turns into an actual problem. This was just to show you in great detail what happens in the standard model. So I think that for today, we can stop here, and I'm happy to take any questions.
Okay. One question.
So from what I understood, so before this computation, you presented the computation so that you had a relation between the Higgs mass and the top mass and the Coulter term. Yes. So that you had no contradiction between the experiment and the standard model. And just before that, you discussed gravitational contribution. And I didn't understand whether if you include the simple gravitational contribution, you would have the same thing, that there will be there will still be a term which you cannot measure, and so you would have no contradiction, or whether there would be a problem.
No, it's exactly, yeah, you would have no problem, because we could look in this way. So like when we computed the pole mass, both for the X and for the W, we have here, let me call it, well, let me just call it mh squared, okay? You have some Lagrangian parameter here. And then for the W, you have this real part of phi WW. And for the X, similarly, well, there is an opposite sign by convention. You have this sigma 2 coming from the top. If you were to add the contribution from gravity, well, you would still be computing, let's say, things like this. Okay, let's say in a regime where T is weak, and I can just expand the Einstein-Hilbert action into gravitons. And then, okay, I'm gonna have some other contribution. Okay, let me call it pi xx gravity. And again, I could write this one and this one in terms of observed parameters. So let's say that I really extrapolate the standard model to the Planck scale. Then I'm gonna get that this thing goes like, and let me also imagine that I've already fixed the counter terms. Okay, so this is all finite. Then this is gonna scale like m top squared. This is gonna scale like m Planck squared. But I still have the problem that the only way in which I can fix this term is by measuring the mass itself. The difference with MW was that this was in relation to other Lagrangian parameters that I can measure independently of MW. Here, so the calculation would, in some parts, reproduce the dimensional analysis estimate, because the dimensional analysis estimate is correct. But you would still be left with an unknown parameter. And in the end, if you ask what is it that I can measure, the only thing that I can measure is a combination of everything. So some people will tell you that this is already, let's say, a manifestation of the hierarchy problem, because you have a piece that you can compute, which is order m Planck squared. So it has to cancel against this piece to give you 100 GeV on this side. I mean, I don't like to call this the hierarchy problem, because this piece comes from the UV just like this piece. You would, if you call this a problem, then, as I was saying before, you would also call renormalization a problem, because imagine that you do the Wilson calculation that I said before. So let's say that I measure mx squared at some scale, and then I integrate out down to a lower scale. What I'm gonna get is that at this scale, the Lagrangian parameter looks like what I measured at the high scale, plus, let me say that I'm integrating out the top core. Now, when I measure plus other stuff, okay, when I measure the X mass, I'm measuring all of this. So indeed, there is a part that it's calculable and maybe it's big, like m Planck square here or m top square here. But there is another part that is big, which is just coming from conventionally choosing the place where you're measuring mx. So when you're measuring this guy at the high scale, you have a UV sensitive quantity. So the fact that these two are of the same size is not a fine tuning. It's just because you chose to measure it at that scale, you see? And the very same thing could be happening here. So you don't know what gravity is doing at m Planck squared. Maybe there is a secret symmetry that we don't know, that is telling you that this parameter is equal to this m Planck contribution, and there is no fine tuning. You see, the fact is that this parameter in some sense absorbs in itself both the calculable parts and the infinite parts. So if you're saying that it's weird that it's canceling m Planck squared, you should say that it's weird that it's also canceling these non-physical things, which in my renormalization scheme would be the 1/epsilons, you see. So either you think that renormalization is okay, which it is, because I mean, of the Wilson picture, and then there is no problem, because here your observable is this period, or you question the whole process of renormalizing in a quantum field theory. But so, okay. Yeah. This is my answer. I should say that this might look very confusing now because of all this renormalization story, etc., etc. But the beauty of the problem is that it exists also at 3 levels. So whenever someone tells you that we find this cosmological constant problem or the hierarchy problem because we're not regularizing loops in the right way, that's completely wrong. You don't even need to read the paper. I mean, which I usually don't. The reason is that, as I stressed at the very beginning, the problem is purely dimensional analysis. And indeed, next time I'll show you in supersymmetry, the problem exists at 3 levels. Even if all loop corrections were all 0, okay, let's say that we are totally wrong about quantum field theory and loop corrections don't exist. The problem in supersymmetry, in every theory where the mass is calculable, already exists at 3 levels. So all these ambiguities that might confuse you are not so important. So I'm discussing them purely because the problem is presented in a wrong way before. It was presented precisely with these calculations. Okay, I don't know if I'm making sense or I'm confusing you more, but well, the bottom line is what I repeated until now, that in an effective theory like this one, you cannot point to a physical problem. End of the story. And in a theory where the X mass is calculable, that we haven't had time to talk about yet, you will see that the problem exists also at 3 levels. So there will not be any of these renormalization scheme ambiguities. There will be no confusion with what's physical or non-physical.
The conclusion of this isn't it that it would be legitimate to accept the hierarchy point in terms of the instead of the sensitivity to a new physics scale, high new physics scale, in terms of the sensitivity of the W boson mass to a new physics scale?
Well, but the problem is that so I don't know. Yeah, I deleted it. But the problem is that the W boson mass is not sensitive to high physics scales because, as you know, a massless vector has 2 degrees of freedom and a massive vector has 3 degrees of freedom. So m equals 0 is a special point. In some sense, there is a symmetry. So when if I were to do the same exercise I did for the X mass for the W mass in dimensional analysis, I wouldn't get m Planck there. I would get the first mass scale that breaks this symmetry, which is mx. Which is not mx, which is the X web. Okay, so in that sense, you might say there is a chain. So if the X mass is sensitive to the I scales, then the W mass is sensitive to I scales through this process. But it's not really true in the sense that only scales that break the symmetry would enter MW. Okay? So let's say that there was that you could in one theory compute the X mass, and there is a piece that is m Planck squared. This piece might enter mx without entering MW. Planck is not breaking the symmetry that protects MW. Okay, I'm not saying it in the best way, but said in another way, when you do restrict yourself to a theory where the X mass is calculable, you will find situations where the X mass is proportional to large scales and the W mass is is locked. Yeah, I mean, until we actually do it, it's gonna be a bit abstract. But one way, yeah. So what, the simplest way to see it is to really do the dimensional analysis estimate, right? Which here we never said that the dimensional analysis estimate was wrong. So the dimensional analysis estimate was always right. We always get these pieces. It's just that there is also another piece that we don't know. And for MW, if you do the dimensional analysis estimate, you're not going to find them plugged because of this extra symmetry. So it's a bit tricky to say that present it as MW being sensitive to a large scale, because in the end it will not be. I don't know if I made complete sense, but that's the best answer I can give you for now. Scaling bias maybe could be better.
You have a question from Pier Francesco online.
Yes. Yeah, so well, the reason why, okay, first of all, I don't know what you're, okay, you can mean two things by saying that we found the X where it has to be. The first one and more important one is that in the standard model, if you, let's say you take the standard model without the X and compute processes like the scattering of 4W bosons or 4Z bosons or whatever. Okay. In the standard model without this, these processes grow with energy. They roughly go like this. And so if you wait, well, there are some factors, but if you go in energy much above the W mass, at some point these processes become non-perturbative. So either you extend the standard model to change this high energy behavior, or at that scale something is guaranteed to happen. So you will see a transition to a theory described by other degrees of freedom. And the simplest thing that you can do is to add the Higgs boson. If you add the Higgs boson, then this amplitude ceases to grow with energy. So in this sense, you are expecting something to necessarily happen below a scale of roughly 4 pi times MW. And you can say that we've seen the X exactly where we expected it to be because of this. So this is the first possible answer to their statement. But the fact that there is this X particle, correct, let's say, mitigating the energy growth of this amplitude, doesn't mean that, I mean, still it's mysterious why there is a fundamental scalar at these low scales with couplings to all these particles, you see? Because of the dimensional analysis estimate we did before. So if you add, so in some sense, it's exactly where it should be, but at the same time, it's also not exactly where it should be. The other reason why they might have said this is because in supersymmetry, so if you really believe that what's explaining why the Higgs mass is small is supersymmetry. Then you expect a bunch of new particles, say a loop factor above the Higgs mass, so again at 4 pi MW. And at the time, there was still hope, well, okay, even now, okay, we might see them at some point, but let's say you really believe that there is supersymmetry at some scale close to the Higgs mass. If you do, then as we will see next time, the estimate for the Higgs mass changes to this, where this is the scale that breaks supersymmetry. And then we will also be able to compute this unknown Lagrangian parameter in terms of other quantities that we know to measure. And so if the symmetry is there, it tells you why the Higgs mass is not all the way up to the Planck scale, but it's lower. And if you do, instead of the squiggle estimate, the actual calculation like we did for MW, then there is a range for the Higgs mass. And this number, 125 GeV, is a bit on the high side, but it's still kind of in this range. So it's actually, this 125 is kind of in an awkward place. It's between what a perturbative and a non-perturbative theory would predict. And we're going to see it next time in more detail. But essentially, it's just that in these theories where you can compute it, you predict it to be coupling squared times masses of these new particles squared over loop factor. If the coupling is of order 4 pi, then you expect the Higgs mass to be at a TV. If the coupling is small, it can be anything smaller. So this 125 is smaller than a TV, so than 4 pi b. And so you could say, okay, it's in the range where you expect it from a perturbative theory with a symmetry that explains it.
Other questions?